Hi everyone, good day. I am ISIEATAS. Today, I will present on my research paper entitled Prediction of Fluid Pattern in a Membrane Reactor for Biodiesel Production. These are the benefits of biodiesel such as economics and renewable fuels. There are few reactors used to produce biodiesel such as batch and continuous reactor. The catalytic membrane reactor is a new technology for biodiesel production. This technology offers an alternative to overcome the common limitations arising from conventional biodiesel production processes. There are few advantages of using membrane reactors such as environmentally friendly process, lower investment cost, overcoming the limitation caused chemical equilibrium, high process flexibility of feedstock conditions, complying with international standards. Objectives are to investigate the fluid flow and velocity profile inside the membrane reactor using CFD software, to evaluate the biodiesel flow pattern of catalytic membrane reactor using different temperatures, and lastly is to determine the flow characteristics of the catalytic membrane reactor. Model drawing and parameter of membrane reactor design for this research are shown as followed. The geometry was meshed using 3 different grid sizes, coarse, medium, and fine, as illustrated in figures below to ensure that the solution was grid size independent. Based on the evaluation of multiple grid conditions, the grid independence test is a procedure used to determine the best grid condition that has the fewest grids while producing the same numerical results. The table, due to its superior performance compared to the other, element 1 was selected for this study. Even though employing a coarse mesh speed up calculations, this approach is still inappropriate for this inquiry. There is no denying that a finer mesh produced outcomes that were better and more palatable. This is because it effectively captures flow information have the most nodes and elements. Flow pattern. The volume fraction of biodiesel refers to the percentage of the total volume of the reaction mixture that is comprised of biodiesel. Figure 7 depicts the fluid volume fraction contours that describe glycerol dispersion in biodiesel oil in 3 different temperature 333 Kelvin, 338 Kelvin and 343 Kelvin as a result of CFD simulations. The flow pattern of the catalytic membrane reactor, which is shown in Table 4.3, demonstrates how different setups will produce different results at various temperatures. All volume fractions begin with 0 in all cases. At 333 Kelvin, the combination reaction of biodiesel and glycerol begins early to rise at a rate of 4.8281 from the reactor's input to its output. In addition, 333 Kelvin and 338 Kelvin achieve highest volume fraction, which is 9.655E1, meaning that it is produce a good quality of biodiesel, plus the red contour show that 333 Kelvin produce more biodiesel than other temperature. A higher volume fraction of biodiesel can increase the rate of the reaction, but can also lead to mass transfer limitations due to increased viscosity of the reaction mixture. The flow regime flow has heterogeneous flow for all temperatures, according to the results. The establishment of an annular flow regime is visible at all 3 flow temperatures. In essence, annular flow is stable and appears as velocity increases. Even though temperature 343 Kelvin have lower volume fraction of biodiesel, it can reduce mass transfer limitations, but can also decrease the rate of the reaction. The optimal volume fraction for biodiesel production would depend on the specific conditions and system being used, and typically requires experimentation and optimization. Velocity. The velocity of a catalytic membrane reactor is the flow rate of the reactants through the reactor. The velocity of the reactants is an important factor in determining the performance of the CMR, as it affects mass transfer, reaction kinetics, and pressure drop across the reactor. The motion of the flow inside the reactor is referred to as velocity in Figure 8 with 3 different temperature 333 Kelvin, 338 Kelvin and 343 Kelvin. The velocity distribution catalytic membrane reactor from different temperature can be seen in Figure 8. The velocity values are indicated by the different colors of contours in agreement with the scale shown on the left side of the chart, where velocity distribution at the non-porous zone follows a parabolic form in both sides of the CMR. During the production of biodiesel, the middle CMR mostly have the highest velocity of each temperature. The velocity is typically higher near the center of the reactor and lower near the walls, creating a parabolic profile. Among three temperature 333 Kelvin have a lower rate velocity, meaning it can reduce the risk of fouling or clogging of the membrane. All components is shown at the steady state situation and the production rate slowly decreases. However, the specific characteristics of the velocity profile can vary depending on the design and operating conditions of the reactor. In addition, velocity can affect the residence time of the reaction mixture within the reactor. A longer residence time can provide more opportunity for the reaction to occur, leading to higher conversion rates and improved product quality. However, longer residence times may also increase the risk of product degradation and side reactions. Based on the CFD simulation, the velocity vector colored by the volume fraction of glycerol within the reactor. The computations began with the laminar model with the liquid at rest to predict the system's hydrodynamic behavior in the turbulent regime. The Kn and fields were initialized. The turbulence model was initiated after the liquid velocity in most reactor areas was greater than 0. The velocity vector at temperatures 333 Kelvin, 338 Kelvin, and 343 Kelvin is illustrated in Figure 9. Table 4.8 displays the three-dimensional velocity vectors inside the CMR. 3 cross-section photos were captured in the ANSYS fluent. Compared to the 3 different temperatures, the vector of each temperature is slightly the same. The reactor's center section experiences a surge in laminar flow after it develops initially at the sparger. A turbulent flow formed around the wall area when the biodiesel production ramped up. A reverse flow to the reactor's bottom is created when EDIS formation is injected at the wall. The highest velocity among the others, 338 Kelvin, produces an unstable flow loop and lowers the residence time for biodiesel production. The highest velocity was observed at the center of all catalytic membrane reactor, but this point came down gently by getting closer to the end of the catalytic membrane, which is due to gravitational force. The velocity and volume fraction analysis in this subtopic is based on the graph drawn due to the vertical plane and horizontal plane, as illustrated in Figure 10. In Figure 11, comparing the observation between all situations can be done by graphing the results from both planes. The analysis allows for the selection of the ideal concentration. Additionally, the graph primarily focuses on the velocity result because, during the transesterification process, the velocity can identify whether the flow pattern in the reactor is highly turbulent or in a low turbulence regime. The plotted velocity against distance at 333 Kelvin, 338 Kelvin, and 343 Kelvin is shown in Figure 10. The figure shows the flow characteristics in the catalytic membrane reactor along the centerline axis. These results demonstrate that the volume fraction along the catalytic membrane reactor. In general, the optimal temperature range for biodiesel production using a catalytic membrane reactor is typically between 60 degrees Celsius and 70 degrees Celsius. This temperature range is known to provide a balance between high reaction rates and good product quality. Among the other temperatures, 333 Kelvin exhibits the largest volume fraction. This is due to a mixture of glycerol and methyl ester reacting as it enters the reactor. The volume portion then dramatically decreases and changes to a constant flow. This can be because the biodiesel has gotten to the pipe outlet. The volume fraction of biodiesel at low temperature is higher than at high temperature due to the change in the physical properties of biodiesel with temperature. These results demonstrate that the volume fraction along the catalytic membrane reactor. In general, the optimal temperature range for biodiesel production using a catalytic membrane reactor is typically between 60 degrees Celsius and 70 degrees Celsius. This temperature range is known to provide a balance between high reaction rates and good product quality. Among the other temperatures, 333 Kelvin exhibits the largest volume fraction. This is due to a mixture of glycerol and methyl ester reacting as it enters the reactor. The volume portion then dramatically decreases and changes to a constant flow. This can be because the biodiesel has gotten to the pipe outlet. The volume fraction of biodiesel at low temperature is higher at high temperature due to the change in the physical properties of biodiesel with temperature. Membrane reactors have encouraging chances for process intensification to enhance the methods used to produce alternative fuels. They eliminate the need for extra separation and recycling units by combining reaction and separation into a single unit. As a result, producing gasoline uses less energy, making also lowering capital expenses. In addition, compared to traditional reactors, membrane reactors can increase conversion and selectivity, eliminate mass transfer restrictions, and have stronger thermal stability. Catalytic membrane reactors allow for simultaneous reactions and separations, leading to higher reaction rates and increased product purity. Additionally, the use of a membrane in the reactor allows for continuous operation and can reduce the need for downstream separation processes. This research found that the optimal temperature for producing biodiesel is 333 Kelvin. Nevertheless, reaction temperature also slightly dependent to other factors such as reaction time, type of oil used, and reaction pressure. More selective membrane toward FAME still needs to be developed in the future to improve the performance of the developed CMR process.